unmute yourself.
Hi everyone. Can you hear me now?
Yes, I can hear you.
Great. Helen, I can't see the chat stream, so if there's anyone who has any questions, could you speak up, please?
Yes, definitely. Yeah, if anyone's got any questions
on the video.
Yeah, if anyone's got any questions, then please feel free to put them in the chat, and then we can answer them after.
My chat window's just turned up. I don't know where that came from. Okay. Okay, so hi everybody. My name's Keir Groves. Sorry, I'm just sorting my windows out here. Yeah, I'm a research fellow at the University of Manchester, and I've been working as a researcher in electrical and electronic engineering for about 8 years. And for the last 3 years, I've been working on robotics for extreme environments. I'm going to be brave in this video, in this presentation, and I'm going to try and use some videos as well. So if they don't work, then yeah, please speak up in the chat, or Helen, please let me know. So my presentation today is about the work I completed while I was on secondment as a visiting scientist at CSIRO in Australia. And normally I work on aquatic vehicles. So the work I did on secondment was actually a bit of a departure from this. And I was working on this ground vehicle you can see here in the center picture. So this was a really good opportunity for me to learn about some different aspects of mobile robotics. Okay, so the agenda of this presentation is very simple. So first I'm going to go through a bit of information about the lab I was working at, and then I'm going to talk about the work I completed while I was at CSIRO, and then some of the outcomes of this work. Okay, so first a bit about where I was working. CSIRO stands for the Commonwealth Scientific and Industrial Research Organisation, and it's Australia's national science agency. So it's a very large and diverse agency. They've got a lot of different sites across Australia. But I was based over here. Can you see my pointer? On the east coast in Brisbane there. I was working in the Robotics and Autonomous Systems group. And in this group, they develop a whole lot of different robots. So they have aerial vehicles. They've got quite a fleet of legged robots they've developed. They automate larger things. This here actually is a Dounreay vehicle, and they work on aquatic vehicles. So this is an autonomous surface vehicle and an autonomous underwater vehicle. So this you might recognize. This is actually a John Deere Gator. It's kind of a farm vehicle, but they've automated that. I think that was a Boeing project. And they also have some smaller ground vehicles like this little science rover you can see at the top here. And the clever thing this group has done is all these systems, they all use a common 3D SLAM system and navigation software. So SLAM stands for simultaneous localization and mapping. It's what a lot of robots do. They generate a map and then they work out where they are in that map. So this term SLAM I use quite a lot throughout the presentation. Okay, so this is the basic setup. So all these robots, they all run on the same autonomy, planning and control system. So we're going to talk a bit more about that in a moment. Okay, so the Robotics and Autonomous Systems group at CSIRO, they're currently working on the DARPA Subterranean Challenge, and they've completed 3 rounds and they have about another 3 to go. So if you don't know a lot about the DARPA challenges, it's actually quite interesting to look it up. DARPA is the American Defense Research Agency, and they essentially can't be bothered to do their own research anymore. So they put out these challenges and let other people do their research for them. So CSIRO are doing this work on subterranean vehicles for them. Okay, so next I'm going to try this video. So this video is about the team I was working with while I was in CSIRO and the technologies that they're bringing to this challenge. And so Nick, the guy who's presenting this video, he's the leader of the DARPA team at CSIRO. And I've been told in the past this video is quite loud, so you might want to turn your speed down a little bit. There's like there's music and American accents, there's all sorts.
multi-agent SLAM for a long time, and this is really a big chance to field test that and push on a lot of the real nitty-gritty details, and really starting to work with that sort of fleet of robots as opposed to going from one robot to many. We are now creating a big global map and using that for global navigation. And on top of that, we're computing 3D frontiers. So any places in that map where we don't have information, or we think there might be an opening, the robot will be attracted to it and explore these frontiers on the scale. We started from a really strong multi-agent localization framework with a spinning ladder. So we built a common perception backpack, and then around that, we really built this multi-agent exploration. So the drone's able to explore by itself, the robots with these global maps, and frontier points and constantly explore.
Okay, I'm going to cut that off there, but I hope that gives you a bit more of a an insight into what goes on at that lab. So that team that was developing all that stuff is about 30 people. They had at least 10 dedicated people just writing software, and then another 10 engineers doing all mechatronic work, and then they have managers and research teams. So as you can tell, it's quite big and well organised effort, and some of the robot systems they've got are quite impressive. Okay, so now I'm going to move on to talking about the work that I did while I was over there in the lab. So the aim of this work was to develop the first mobile robot that can autonomously map a radiation environment and at the same time avoid areas it finds to have high radiation. So functionally, what we wanted out of this robot, we wanted to be able to put it into an unknown radiation environment. So that's an environment that's unknown in terms of where radiation sources might be, and unknown in terms of the physical environment that the robot's operating in. So a good example of this would be a disaster environment where you want the robot to go in and autonomously explore this 3D environment and produce you both a geographical and a radiation map of that area whilst minimizing the dose that the robot receives. So the plan for doing this was to take an off-the-shelf ground robot. We didn't want to go developing a whole new ground robot because there's plenty of those, and then add CSIRO's SLAM system to their localization system, and their autonomous navigation software, and put a radiation detector on that robot. And then I'd write a software package on top of that that links the radiation detector to the navigation software. Okay, so now a bit more detail about that system. So we started with this ClearPath Husky robot. Some of you might be familiar with it. It's quite a standard robot. So everything apart from what's on top, this is the bottom part, is the Husky robot there. So the second component is the CSIRO SLAM pack. So that's this part here that looks like a bird cage. And so this is the bit that gives the robot a geographical map and the location within that geographical map. So the component SLAM pack, it's got a Velodyne LiDAR. This is a high quality LiDAR, and it's actually inclined at 45 degrees. Then they spin it round as well. So that means you get really nice coverage of the 3D space. There's an IMU in there, which stands for inertial measurement, which is essentially just accelerometers and gyroscopes. And the SLAM, so the software, runs on board this pack as well on a dedicated graphics processor. So the idea is you can put this pack on any robot, you power it up, and it gives you a map, and it gives you your location within that map. Okay, so these two parts, you've got a robot that can move around. So the next thing is it needs to know how to navigate. So that's part 3. So that's CSIRO's 3D navigation software. So the software that's on that robot is exactly the same as you saw in the video. So the robot's navigating around. It runs the same software. I put it on board this Husky robot here. The fourth component is the radiation detector. So you can see the radiation detector is actually over here at the front. So it's one of these Radii G10. So you might recognize this. It's just a standard wearable radiation detector. But this one's actually been modified. So instead of measuring gamma radiation, it measures radio signal strength. And then to go with that, we have these called safe mini sources, and they just emit radio waves. So we have this nice environment. There's a simulated radiation environment, but it's safe for the robot to navigate in. And the beauty of this setup is that we can, sorry, let me get that one. Is that if you want to change this from a simulated radiation environment into a real radiation environment, all you need to do is change this modified detector onto a standard detector, and it will work in a radiation environment. So then the final component is the radiation mapping and avoidance software package that I wrote to connect up the radiation detector and the navigation software. So what this software does is it records the radiation strength from the radiation detector and the location of the robot in the SLAM pack, and it uses that data to modify something called the cost map, which the robot uses to navigate and path plan, and I'll speak a bit more about that in a moment. And so now with that software package on there, the robot can plan around all of the normal obstacles it'd normally avoid, but also it plans around radiation as well. Okay, so I did a load of experiments while I was out there. Some of them I put sources inside this warehouse, and some of the experiments I did outdoors. So in this one, I put some radiation sources, you can see here, outside this warehouse. I'm gonna start with the robot in the warehouse and then drive it out, and it explores this area and finds and then avoids this radiation. So I'll just play this video. This is sped up a bit. I think this whole test was about 15 minutes. So you can see the robot is near to this radiation, and now it knows it's there, it will avoid it. So first the robot explores this this area here, and then it moves up into this area with these bushes here. So this is kind of a semi-structured environment. You can see there's some gradients there. So the thing that's kind of impressive about this video really is how well the robot performs, even though it's come from indoors to outdoors. It's come from a nice flat environment onto this kind of loose gradient here, and I also send it up into this grassy area here, and there's some funny poles here that it manages to avoid as well. Okay, so now I just send the robot, I think I tell it to go back home now. It'll come back and avoid this radiation source and this one too. So it's going around that radiation source there. Back into the warehouse. Okay, so that was just a overview video. So now I'll try and show you kind of what's going on a little bit under the hood of that of the software. So this on the right here, this is what the robot is called this output essentially. This all these pixels, this is the global map that the robot generates, and the red dot is where the robot is in this map. So this is that warehouse that you could see in the previous video. So, and on the left, this is the cost map. This is the cost map that the robot uses to do its navigation. So you can see here this pink part here, this is their cost, which actually is wall, so the robot knows it should navigate around that wall. So there's that radiation source out there, which is coming into play in the moment. So pink is high cost to the robot, blue is low cost, and black is no cost. Okay, so I tell the robot to come out, and you can see I'm laying out some waypoints here. So I put a waypoint out quite close to that radiation. So the robot it has to go over there and it'll go past this radiation area. So you can see now it's something close, it's time to take down to low cost near that radiation source. And as it passes this radiation source, it will start to increase that cost that it puts down. So you can see now this blue starts to turn to red and pink where the cost gets so high. So the robot's now met that. Questions in the chat?
Yes, if anyone's got any questions, then if you post them in the chat. Oh, so I don't know if you can see the chat here, can you?
Yes, I've got it, yeah.
Yeah, so there's one from Mark. Have you given thought to commercial exploitation opportunities?
No, it's not something we've actually considered yet, and at the moment, that the system is very expensive because it's like a research project and it's got a lot of hours involved in it. But I think that would be something that's possible in the future.
Can you see the question from Marty? Did the
Yes.
slam pack rotate the Velodyne?
Yes, it did. Yeah. So the let me just whiz back a few slides. So maybe the audio was bad during this part. So this is the slam pack here, and you can see the Velodyne. It's inclined at 45 degrees, and yeah, they also rotate it. So you get a really good 3D coverage. So I think you can probably see at the start of this video. So that's kind of with the robot still, this is the kind of 3D coverage you get of the area, which is very good. So let me just get back on the chat.
So there's a question, is any of it either open source or available for RAIN to use?
There's the stuff that we did on it, so our radiation avoidance package, that'll be available for use by RAIN, I think, but the side of it that CSIRO developed, so the SLAM pack and their navigation stuff, is not open source, and I think they're commercializing it.
What are the next steps for this project?
Well, we actually have people in Manchester, so Andy is working on some similar stuff to this, so I think he will probably be picking this up and carrying on with it. But we also have people on R&E on our grant that runs alongside RAIN, working on very similar stuff. So there's quite a few people in different areas working on this sort of thing.
Which sensor did you use for the methane detection on the robot in the overview slide?
We didn't have any methane detection on the robot.
Okay. Can SLAM algorithms be used outside of robotics, such as on a radiological operator?
Yes, so that I should have mentioned that pack, they actually have just a backpack that you can use as well, and they have another handheld version of it too.
I'll just do a couple more. Is the robot autonomous or manually controlled, or both?
Yeah, it's autonomous in terms of the in between waypoints. So I tell it go to this point, and then it autonomously navigates its way to that point, doing all of the obstacle and radiation avoidance.
And how easy was it to interface with the SLAM?
From a hardware point of view, there's not a fully commercial system yet that they've developed, so it did take a bit of work to interface it, and you have to set up quite a bit of stuff to get it to work. But I think they're actually writing a load of user manuals and things for that pack at the moment.
Okay, great. I think we're going to leave the questions there, just because we need to move on to the next speaker. But if you want to reply to people in the chat, then feel free to do that, Keir. Or we might be able to come back to it
if
at the
there
end.
were any elements that were unclear or jumpy and anyone wants me to go through, just let me know and we can do that offline.
Brilliant. Cheers, Keir.
Okay, thanks everybody.
Yeah, thanks everyone for all your questions. It's really good to know that people could hear enough to have things to ask. Matthew, do you want to?
Hello, can you hear me?
Yes.
Okay, shall I leave my video off and just share the screen?
Yeah, I think leave your video off and hopefully that will help.
So can you see the presentation?
Yes.
Brilliant. Right, so good morning everybody. My name is Matthew Nancekievill and I'm a PDRA on the RAIN Hub working at the University of Manchester. And today I'm going to talk to you about active deployment at the University of Manchester's tracked robotic platform at Dounreay, and also a summary of some of our aquatic robotics research. So just quickly, the way we're going to do this is I'll go over some aims and objectives, some nuclear environments that we've kind of worked in or we're working in currently to give you a flavour of the sort of robotics we do. An overview of the Vega robotic platform that has done some of these deployments and is aiming to this. An active deployment we undertook at Dounreay in March, just before the lockdown, and then some aquatic research before talking about getting involved in some collaborations. So just general aims of what we're trying to do is developing a set of robust, cost-effective robotic platforms or technologies capable of characterizing really quite hazardous environments, so cluttered, GPS denied, enclosed, and sometimes submerged. So some of the things that we need to take into account for this are developing the robust robotic platforms, high accuracy localization systems, and then putting a load of different payload sensors onto our devices through the needs of our industrial partners and collaborators, so 3D reconstruction, sonars, thickness gauges, pH sensors, all of that, and also understanding how radiation affects the electronics on board. So one site that we're working towards and we were hoping to do a bit of in the next couple of months, but is kind of put on hold for obvious reasons, is some work at the Magnox site in Dungeness down in Kent. So there's a little bit of concern that there's potential water ingress into some of the basements of the reactor buildings, and so we need to justify the structural integrity and just couple it with some general inspection and maintenance strategies. The big things that are needed out of this are photographic survey of the void areas, 3D laser measurement survey, and also a gamma radiation survey. And that's relatively consistent across multiple sites. But I'm mainly going to talk about Dounreay today. Dounreay, located right at the north of Scotland, absolutely beautiful area when it's sunny, and it contains 5 reactors, but it's all in shutdown now, being maintained for integrity and hoping to decommission over the next few years. More specifically about the task that we've been given in helping Dounreay. This is a very simplified representation. I'm not going to talk about scales and whereabouts on site this is, but in a broad overview, there is a relatively enclosed area with a big pipe going down the middle, and off this pipe are support branches. So if I get my laser pointer, so this is the top-down view. Looking down, these red dotted lines are manhole covers. We have this pipe down the middle, and these branches coming off, which actually come up away from the pipe a bit and down a different path channel. So we're looking at operating a robot in this area in the corner here, and we're kind of constrained with size and kind of also deployment mechanisms. So we need to deploy down one of these manhole covers, which are a certain size. We need to set up containment, and we're going to operate in here. Now, what Dounreay have asked us to look at are a visual inspection of the area. Are there any blockages, debris, leaks, similar, that sort of thing, whilst also doing a complete radiological survey. And we're talking gamma, neutron, alpha, and beta, but we're mainly dose rate information. We're not really looking at spectroscopy right now. And Dounreay have agreed to provide all the relevant sensors for the robot. One of the really interesting things about this is also taking samples or swabs of areas that are kind of highlighted as areas of interest by Dounreay personnel. Initially, this may be 30 to 50 samples, but during our visit, this may actually come down to less than 20, but it's one of these that we'll see how it's going. Also, we'll be given about a week to complete the tasks. The data obviously has to be left on site. They're going to be handing us a hard drive. Everything has to operate off of. We just get a human readable format out of all the data. All operations are under remote control, no autonomy, and we need to have a fail safe. So if a wireless link is broken, because at the moment this is all under a wireless and batteries, we need some way of retrieving the robot. Hopefully, once this is all complete, we can have some sanitized data to publicize a few weeks after deployment. Before I talk a bit more about development of the robot, I just want to mention the team. There's quite a few of us working on this. So I'm Matthew, and then going left to right, and then downwards, we've got Tom Wright, Bart Garcia, Nathan, Tom Johnson, Andy West, and Ben Bird. supervised by Barry Lennox and Simon Watson. And we've also got help from Innovation to Commercialization with Frank Allison and Stuart Brown. So the Vega robotic platform, here we go, is a small tracked robot. You can see that the base of it is about 30 by 30 centimeters. We have a range of different sensors on board. So as Keir was talking about the Radii G10 for gamma radiation, we've got 2 EPDs that Dounreay have provided to us for neutron and beta. And we also, that's not shown on here, is a Radii SX, which will be connected to a Ludlam probe to detect X-rays. The other main sensors that are of interest on the robot are the 2D LiDAR for the SLAM and positioning, and also an RGBD camera to give us a bit of a point cloud. We're going to be working in quite dark conditions, so having that IR projector will be quite useful for avoiding obstacles that are below the LiDAR. And then we're also using an open manipulator robotic arm for sampling of the floors and walls. And the way we're going to do the sampling is we've been given this puck swab, which you can see on the right has a little bit of foam, which helps with a bit of compliance in case we're shoving the arm into the floor. A bit of filter paper will then be attached to this, either a bit of sticky, tacky adhesive or an elastic band, because the filter paper is a bit bigger than the swab to hold it down. We initially wanted to hold multiple bits of filter paper samples on the robot, so we could do multiple samples at one time. This looks quite difficult, especially with cross-contamination, and you can see on the top of the robot it's getting quite packed. So we're likely to pick up a swab, take it back to an entry point, get it changed by an operator, take it back out and do one swab at a time. But this is under constant review. So some lab tests of this. It's just a very simple set of videos of the robot moving about. The green on the right represents no radiation, and I'm using the same radiation or fake radiation source that Keir was talking about in the previous presentation. So as it gets near, things start going red because you're really, really close to radiation, and then it starts moving away. But one of the interesting things to take away from this is the sensor only detects radiation when it's, well, it starts showing you that it's detected radiation when it's really close to the source. Now, as it's driving away, you'll see that it's saying there's radiation where there wasn't on the way up. And that's because there's about a 10-second integration time. So one of the ways around this is just driving really, really slowly. Otherwise, we need to do some sort of post-processing interpolation to work out that if it started there and finished there, it's probably somewhere in the middle, based on the time it takes to get our radiation results. So at this point, went to these are some pictures from Dounreay, and I want to take this moment as one of many to thank Dounreay for how amazing they've been. We thought that initially we were going to be demonstrating the robot in an office sort of space, but Jason Simpson, who is here on the left, organised us to go into an active waste store. So you'll see these containers here full of gamma waste, and we pass the Vega robotic platform down the middle. And this is supposed to simulate as close as possible, within reason, the sort of environment that we're going to get in it. It's going to be very enclosed, so you're very close to the walls, and we get a lot of light in this environment. In the real environment, we won't have much light, but this is as close as we could get. Here's Barry pointing at the screen, and that's where we're operating the robot from. So this is the only data I've got off. I was told I was allowed to share this in. This is the radiation results. So you'll see this is slightly redder than here, and it's because it's slightly closer to the gamma store. We just drove up and down and took measurements, and so you'll get slight fluctuations in readings. We're not talking high radiation. This is in my feet, so we're talking very, very low level type events, but this kind of demonstrated that the whole system worked. Again, another big thank you to Dounreay. Here they all are on the yellow high vis. Jason Simpson, who's hiding away at the back there, and also Greg Cormack helped us a lot in communicating and getting this going. It was really, really, really nice to have this big push and to get it all done by March, and luckily we got it done before everything shut down. So what the plans are now is we'd like to go back. It was initially designed for early June to go back for another site trial for a day or two, and then to go back a couple of weeks later for a whole week to actively deploy. As you may have guessed, this may get pushed back, but we'll see what happens. It's also dependent on Dounreay personnel completing a preliminary inspection, so they're going to lift one of the manhole covers and have a little look, see if there's an easy place to deploy the robot. It may be that we have to deploy somewhere else, and because it takes a minimum of about a week to set up containment around each of these manholes, it may require a bit of moving around and checking. Kind of classic industrial requirements, so safety cases, risk assessments, and further development of the robot. We're getting a lot of help from Dounreay and I2C for safety cases and risk assessments and kind of project management of this on an industrial sort of specification. And some of the further development of the robot that me and the rest of the group are doing are arm control for swabbing, developing software for the proprietary EPDs, which are unfortunately discontinued. So I have a bit of basically, we need to work out a way of integrating with the robot these EPDs. Simple things like removing sharp edges. I was given a lot of gloves to try and put a robot together and take it apart with those gloves to modify the design for anything that I need to make sure fingers don't get trapped. We also need an easy cartridge style battery. Dounreay staff are going to be operating the robot on the containment side. So we'll need to have a really easy way of removing the battery and replacing it, especially in all those gloves, whilst I'll be teleoperating the robot from just outside containment looking through a window. So I'm now going to move on to a summary of some of the aquatics robotics research. This is something I've done a lot of in the last few years. A lot of you have heard of the Avexus, which is a small submersible designed to get through 6-inch access ports, moves in about 3 degrees of freedom. And it could take a payload of just over 1 kilo with no additional ballast. This was achieved with we did some tests in Fukushima with a sonar on the bottom that weighed about 1 kilo. You get a live HD camera, and right now it's acting as a research platform to integrate sensors and control algorithms. So we had a PhD student working on interesting control, and we do a lot of work with Lancaster University on radiation detectors and integrating them in the system. We'll see how these videos work. They'll probably be a bit choppy, but just an example of this was a test done in a trigger reactor in Slovenia. This was it driving around before we turned it on. As soon as we turned it on, we had to hold it still in case it became irradiated, failed, and floated to the surface. But it's designed to work in these cluttered environments, and we'd integrated here a sensor from Lancaster University to do some spectroscopic analysis of the radiation sources coming off of the reactor. So this was also to do radiation tolerance testing. It lasted for about 80 gray, 80 sieverts, where the power supply went. A lot of the other components would last a bit longer, but if the power supply goes, then the power supply goes and you can't operate. So it's something to work on. But yeah, we're hoping to do some more tests with Lancaster in the future, but it's all been put on hold because of shutdown. Another bit of work that we're doing is using that Avexus underwater. We need an accurate way of positioning it. Not the easiest thing, and it's often done with acoustics, which are accurate to maybe about 1 foot if you're lucky. So we're developing a vision-based system with a camera near the surface of the water that will visually track a marker that is on the ROV. So using the Mallard system that was originally developed by Keir, who spoke before, we're going to have that float on the surface, and it knows its position to an accuracy of about ±2 millimeters, and then extrapolate some XY coordinates of the Avexus underneath it. And then obviously we have the depth on board of the Avexus to get Z. And all sorts of gymnastics of positioning to work out roughly where it is, hopefully to a higher accuracy to within a couple of centimeters in comparison to acoustic technology. One of the difficulties is verifying that this system works. So we've purchased a QualiSys system, which for those of you that know the Vicon system or motion capture systems for movies, is an underwater tracking system that is kind of millimeter accuracy. It's due to be installed the day after shutdown, so it hasn't been installed. But we're going to use this to verify our localization system and also some kind of underwater automation potentially. It's part of a growing facility, and I believe that if anybody's interested in collaborating and using this bit of kit, that we can have a chat. Yeah, it's a great bit of kit. So just finally, collaborations. We've set up a bunch of robotic platforms. So here we've got the Vega robotic platform, the Avexis, the Mallards, we've got a Blue ROV, and we really like integrating technologies, payloads, and all sorts of different things. We can offer demonstrations and deployments on site or in a lab at relatively short notice, lockdown willing. So yeah, basically, please get in touch if anybody's interested in using any of these robotic platforms for issues on site, or if you can see potential for integrating a new novel payload or sensor. So thank you very much for listening.
Thanks, Matthew. We're a bit tight for time, but we've already got a question in.
Okay.
Does the robot gradually become radioactive, and does that affect how you can use the robot and how much work it can do?
So it depends on the environment that you're in. So gamma radiation won't make the robot radioactive. Over time, it will degrade to stop the electronics working, but it's over a much slower time than humans. If you're operating in a neutron environment, depending on the flux, it can affect what you're doing, and it can make the robot radioactive. So I put it in a neutron flux, and it made the communications a bit, for want of a more scientific word, iffy. And then over time it became active, and what became active in it was the gold and the components. So then it had to be left for a couple of weeks before it could be used again. But hopefully in most of the radiation environments we're going in, it shouldn't affect the operation of the robot. Great.
We've got a question about battery life.
Okay.
It's for the Vega.
So battery life for the Vega, without the arm, it was about 4 hours. We've not done a lot of testing with the arm because the arm is always on, so it's always drawing a bit of current. But we're assuming somewhere between 2 and 4 hours.
Great. I can't see any other questions in there, but if anyone has got more questions, then feel free to put them in the chat, and I'm sure that Matthew can answer them after. Liam, if you want to get your screen on, and you still there? Yes.
Hi, all right.
Hi, Liam. Brilliant. Yeah, you can hear you.
Can you see the screen and everything?
Yes.
All right, perfect. I'll leave my camera off because the audio is pretty good on that one.
Yeah.
So, yep. Hi, I'm Liam Brown. I'm a PDRA at the University of Manchester, and I'm going to talk to you about the Prometheus project. So Prometheus is a UKRI Innovate UK funded project, and it's a multi-partner project, and all those partners are down the bottom of the screen here. So some universities, some companies as well. I'll give you a bit of a hint. It's not actually nuclear focused at the moment. We're looking at mine environments, but this technology could be applicable in lots of different areas once it's developed. So the catchline for the project is a reconfigurable robotic platform with advanced sensing for confined spaces. So to give you a bit of a background to the project, there are train lines built across the whole of the UK. Now, some of these train lines are undercut or are near old abandoned mines and other underground voids. So to give you an idea of the scope of this sort of problem, there's around 5,000 abandoned coal mines alone near the rail infrastructure. And these will require regular inspection to check that they're not going to subside or cause any other issues to the rail network. So if they can access these mines and it's safe to do so, they can send workers into them, they can manually take measurements, scan them, and work out the chance of subsidence, or if they're going to have any issues, and if they need to implement anything to stop that from happening. But a lot of these mines are a few hundred years old, and they don't have access, or they don't know where the entrances are anymore, so they have to sink boreholes into the mines to try and scan them. And what they do is once they've sunk a borehole, a 150mm borehole, typically, they put down cameras and other sort of LiDAR sensors to try and build up a map of this mine. And you can imagine that if you go down into one section of the mine working, it's unlikely that you're going to be able to see the whole working from that one borehole. So they have to sink multiple boreholes, 10, 15, 20 boreholes to develop a map of this whole mine. Which gets pretty time consuming and very expensive. So it kind of ties into the aim of the project. So that's to develop a reconfigurable or a robotic platform, so a UAV in this case, that's deployable through one of the boreholes, and it's capable of completing this 3D survey that they want, so they can look for any issues with the mine. Whilst traveling beyond visual line of sight underground. So that's because it's underground, we're looking up to 35 meters deep. It's unlikely that a pilot's going to be able to see it at that distance. And it's going to have to be autonomous as well, because we couldn't sustain an RF link if it goes round into the workings. So to give a bit of a better idea of what we're doing, I've made this GIF. You can see there's an underground void near the train tracks. In this case, it's underneath, but it just has to be within a certain distance for it to be a possible issue. And what they do is they turn up, they sink a borehole, they then deploy a mechanism to drop the robot into the void, which unfolds, flies around the void, scans it, explores it, and then is retracted from it. And then they can use that data that is gathered for post-processing later on. So just going to give you a bit of an overview of what I'm going to talk about. So we've done a couple of demonstrations as part of the project. The first is a confined autonomous flight, and then the second is an autonomous mission. I'll try and point out the differences between those two things as we get to them. Then I'm going to move on to talking about the Titan prototype, which is the actual folding design, and then just the future work of the project. So this was the first demo, which was the confined autonomous flight that we did at the University of Manchester. So the first step for this was to build a representative prototype of that folding, of the final folding version, the Titan prototype. So that's this PROM 001 that's shown in the picture. Now the idea of this prototype was it was quick to build, and it because it doesn't fold. But it's representative of the final one because it's the same weight, size, uses the same hardware components, and so we could integrate the work from all the partners on one platform without needing that final design. So that was the PROM1 UAV. So the aim of this test was to do a confined autonomous flight. And this is a basement at the University of Manchester. It's fairly low ceiling height, fairly tight, and you can see there's a Vicon setup in there, which I'll talk about in a minute. So we scanned this basement with some LiDAR sensors, and then manually generated a path that we wanted the drone to fly. So we knew it was a safe path. We knew it wouldn't deviate into walls and that sort of thing. So we're going to fly the Prometheus drone with this Dragonfly sensor pod. So the Dragonfly sensor pod was developed by one of the partners on the project, Headlight AI, and it actually produces sort of a 3D donut of depth information. You'll see a bit of a stream from it later to help explain. And then we're using the Vicon system as position feedback for the drone. So obviously we couldn't put a Vicon system down one of these mines that we're looking at. So down the line, we are going to look to develop SLAM or positional feedback using the onboard sensors. So this is the first demo, or a video of the first demo. So this was the pre-scanned environment that I was talking about, the basement. You should be able to notice in the corner when it pans up the sort of racking that was at the back of the room. So some of the more eagle-eyed of you may have noticed that the UAV that we're using is different to the Prometheus one. Again, it's a similar size and weight, but we had some issues with the first prototype. So that was a manual takeoff using the position feedback, and then we switch it into autonomous mode to fly the trajectory that we manually inputted. So the deviation in height there is actually just from the effect of the ground effect and ceiling effect that's going on to the robot, and the fact that because we're using a different platform than intended, it wasn't as well tuned to the payload that we put on it. So hopefully that will be reduced down the line. So it fairly successfully followed that path that we inputted into it. So this is the data from the Dragonfly sensor. So this is just the raw data from each of those, from each sensor in the pod. You can see some of the racking at the back that it's picked up, and the shadows of the tripod cameras on the walls. So yeah, that was the first demo. So the second demo was this full autonomous mission. So the differences with the previous one, we were looking at trying to fly a path that was generated from our path planner, as opposed to a manual one that we knew was safe. So what we did was we modeled the environment that we were going to fly in. In this case, it was the Bristol Robotics lab down at the with the University of Bristol, and we built this simulation environment that's shown in the picture. It was a sort of 8 meter by 4 meter area, and then we put a 1 meter wide 1 meter object in the middle of it. And then what we did was we ran a simulated sort of mission in this unknown area. So this was what the drone could see to start off with. It then explored this area, and what we did was we took the path from simulation, the path that the drone flew in the simulation, and injected that straight into the real system. And then we flew that path. So again, we were doing position feedback from the Vicon system. So this was just a picture of what the environment after the drone had finished exploring. So it managed to map that full environment. Now the path that the path planner generated is shown in this top picture here. It's kind of difficult to tell, so it's a similar shape to this Gateshead Millennium Bridge, so 2 sweeping arches. So I'll let this video run. So yeah, this is the full autonomous mission, that autonomous takeoff. It then tracks the set points. As it hits every one of those bumps, it sort of jolts the drone a little bit, which is something we need to look at smoothing out in the future. But by the same right, we don't want it to deviate from the path too much, because if you're in a very confined environment, you don't want it drifting into walls. So that was at ×2 speed. So yeah, that was the second demo. So the next thing is the sort of final fold-in prototype that we're calling the Titan 1 prototype. So it's shown, or a basic render of it's shown here. So it's got the folded up bit with the arms down, and then the unfolded one here. So we're aiming for a flight time for the system of between 10 and 15 minutes, which is dictated by the final weight of the system, which isn't completely determined, as we're still constructing the drone and we're unsure exactly how heavy everything's going to be. So when it's folded up, it is around 130 millimeters in this diameter. That's to allow it to fit down of one of these 150 millimeter boreholes, but give us sort of a bit of wiggle room to allow for the deviation in the borehole. So when they drill these boreholes, they're not, you know, they're a real thing. The drills skip side to side, and there can be jolts of rock and stuff, and they can twist and turn a little bit as you go down. So that's why we've added that clearance in there. As it unfolds, it actually gets a little bit smaller. So the total length from top to bottom goes from around 0.5 meter to around 420 meters. And then its unfolded tip to tip diameter is around 3/4 of a meter. So as well as all the fold-in hardware and the actual things required for flight, it has all the onboard computing and sensing required for sort of keeping itself in the air, as well as mapping this void. So I'm just going to move on to the future work of the project. So as I mentioned before, we need to start to develop that SLAM system. So how we can use the onboard sensors, the Dragonfly sensor pod, to give us an idea of our location and stop us flying into anything that we shouldn't. Then we need to work on the deployment mechanism, the thing that's going to put the drone, carry the drone down the borehole and place it into the void, where the mission will sort of start from and where it will dock and be retracted from. And then we need to start to manufacture all of that. So manufacture the Titan 1 prototype as well as the deployment mechanism and all the other bits that we need. So the project is currently running until April 2021, and we have 3 planned deployments as part of the project. So July, September, and February. Obviously, in the current situation, we're not sure what's happening with those dates, but hopefully we'll still get to do them. So that's me. I've finished a bit ahead of time. So are there any questions?
Thanks, Liam. That was great. Oh, there's a question in. What type of flight controller is it?
So currently we're just looking at off-the-shelf flight controllers. So we're looking at a Pixhawk 4.
What's the flight time for the Titan 1?
So that was in this slide. So between 10 and 15 minutes, but it's sort of quite heavily dictated by the final weight of the prototype, which we're unsure of yet. Like, this is still in the design phase.
Okay, great. Could this be deployed through a vertical port, and can it be recovered?
Yes. So the aim is to be able to deploy it. Sorry, I'm just scrolling back to try and find my little GIF. Is to deploy it through the top of these mines. So it should be shown in this. Yeah. So you drill the borehole down. It has a vertical deployment, and then it flies around. And then it has to be removed from the mine as well, because this is going to be flying beyond visual line of sight, and autonomously we won't have a data link to it, because you can imagine if it goes around a corner in a mine working, we can't maintain connection to it. So that all that data that it's gathering is stored on the drone itself. So yeah, it has to be recovered.
There's a question here. Have you considered simulating the environments of Mine in Germany or Waste Isolation Pilot Plant in the United States? They're both salt formations storing radioactive waste, to demonstrate its potential use for geological disposal projects.
We haven't actually, because our current focus is on abandoned mines for the project, but we are looking at simulating some information that we have of real scans of mines and that sort of thing. And yeah, I think it could be, that does sound like a thing that we could look into for potential commercialization in the future.
Have you considered recoverability under failure?
Yes, we've basically been told you're not going to get it back. So these boreholes are, the size of the drone changed so dramatically when it's unfolded that even if you could manage to find it wherever it had crashed, which is again very unlikely, it'd be really difficult to get it back out again without completely destroying it. So yeah, we're working on the theory of, if it crashes, it's staying down there.
There's more questions coming in. What are the weight/power requirements, challenges for processor for the AI planning and sensors? Does that make sense? What are the weight power requirements for processor for the AI planning and sensors?
So the weight requirements, again, they're shown on this slide in terms of flight time. I know the size and all that is being taken into account in the AI planner, but that part of the project is being done by one of my colleagues at the Royal Holloway University. If you want to drop me an email afterwards, I can connect you to him.
Cheers. Another question here. Has a survey been carried out of a typical mine to understand any potential for strong turbulent airflows or magnetic effects that might affect an off-the-shelf flight controller?
That's a really good question, actually, because it's incredibly difficult to work out the effects of flying in, ground effect or walling effect or ceiling effect. There hasn't been many studies carried out to actually dictate what that is. And if you're in a very confined mine, you may actually be flying in all 3 of those things all at the same time. So to answer your question, no, we haven't looked at, we haven't carried out any surveys, but we are going to do some real world tests in mines where we can try and measure that effect, as well as sort of lab based, more methodical tests to try and work out the effects of them.
Still questions coming in. Any idea of final commercial cost of a unit?
No. So at the moment, it's still very early prototype stages. So I couldn't answer that question. Sorry.
How difficult is it to train an operator with no knowledge of robotics to carry out such inspections?
So again, good question. We're planning to try and make this a sort of turnkey system. So our spec says that it needs to be one person operable, and that operator doesn't need to be skilled. So the idea is you turn up, the borehole's already drilled or has been drilled by someone else, and you get the system out, put it in the borehole, and then you tell it to go. And so it doesn't require any manual flight. The system's going to be fully autonomous. So yeah, they should require basically no knowledge of robotics. There's the potential to need to change batteries and that sort of thing, but very, very low level things.
Another question. Could this be used to plan a repeatable flight that would then be used to compare data?
Yeah, definitely. So we're part of what we're considering is if these mine workings are bigger than what we can cover in 1 10-minute flight time. So in that case, you may want to explore for the 10-15 minutes, come up, change the batteries, redeploy it, and then it take sort of carry on from where it was before. So either use that path that is already planned or actually replan a path in the environment it already knows. Or again, in the future, you could come back, fly the same path, and see if there's been any changes to the mine environment.
Great. I think I'm going to finish there now, just so we finish roughly on time.
Okay.
Thanks everybody that joined us. Thanks all the speakers. If anyone has got more questions, I don't know, Liam, I think that the room will be open for a few more minutes if you want to answer anything that comes up.
Yeah, I'm happy to stay on the call, or people can send me an email if they want. I'll just drop my email into the chat if
Brilliant.
that's easier.
Yeah, that's a good idea. Yeah, if anyone does want to follow up with anything and can't find an email, then feel free to have a look on the RAIN website and get in touch through the mechanisms on there. Feel free to sign up to our newsletter because we'll send information out on there and on social media and things there as well. So thanks everyone for joining us today, and stay safe.